Okay, good evening, dear students. In last class, we discussed about the determination of elevation in the boiling point by Landenberger's method. This is very important for 5 mark question. Okay, in today's class, I am going to discuss about the depression in the freezing point. The relationship between already done the derivation in elevation, the relationship between the elevation in the boiling point. Here, the relationship between in the freezing point, depression in freezing point and lowering of vapor pressure and molecular mass. Ready? This is also very important question. Relationship between depression in freezing point, depression in freezing point, depression in freezing point and lowering of vapor pressure and lowering of vapor pressure. Lowering of vapor pressure and molecular mass and molecular mass. Here, this is a very important. Here, the relationship between depression in freezing point and lowering of vapor pressure and molecular mass. First of all, I will run here the diagram of this or graph of this relationship between depression in freezing point and lowering of vapor pressure. This is the point B and this is the point A, this point. Here, solid solvent. Solid solvent. This curve is a solid solvent and this point is A and this point is B. And here solvent means liquid solvent. Here the point is and this point is a B point and this point is D point. A, B, C, D and this one is B. Here this is a solution. This is a solution. You already know the solution curve is like always below the solvent. This is solid solvent. Solvent means it is a liquid solvent. This is a point B. And here this is a C point, this is a D point, this is a solution D. And here the versus this case this point is D, a T. Here, this is temperature, and this is a vapor pressure. Okay, I know already this difference is delta T, and this is P2 and this is P1. This curve is P2 and here this is a P1 and another this this is a P0. Here this curve is solid solvent here P2, solution P1 and solvent here P1. Here the temperature is P, the here this temperature is T. Okay. See this graph, explain 5 to 6 lines about this diagram. Okay. First, what is meant by freezing point? The 1 mark question is very important. The definition of this freezing point. This is 1 mark question. The freezing point of the temperature, solid and liquid state of a substance. The freezing point of the temperature at which the solid and liquid state of substances have the same vapor pressure. Here have the same vapor pressure. That temperature is called as freezing point. I write here the definition of freezing definition. The freezing point is the temperature. Freezing point is the temperature. Important question. This is 1 mark question. Freezing point is the temperature. This freezing point here one type of the temperature. This one temperature at which you see here, at which here one is a solid and another this is a liquid. The solid and liquid, this temperature at which the solid and liquid state of the substances, the solid and liquid state of a substance, have the same vapor pressure. Have the same vapor pressure. Same vapor pressure. Same vapor pressure. That temperature is called freezing point. See here, definition of this freezing point. Right? The freezing point is the temperature at which the solid and liquid state of a substances have same vapor pressure. That temperature is called as the freezing point. Freezing temperature. Right? When asked in your examination, this question, you write this. Okay, this figure is freezing point depression figure. Right here, the Here is freezing point depression. Freezing point depression. Here the freezing point of sun. This is a freezing point of sun. Here the vapor pressure curve P was here one is a solid and another is a liquid and another the curve line below the this solvent curve. This is a solution. You see this diagram and explain the solvent curve. So two solvent curve, one is a solid and another is a solution. Sorry, one is a solid and another is a liquid and third curve is a solution curve. Explaining here the vapor pressure of the curve. Here the vapor pressure, here presence of vapor pressure according to this axis and according to this axis present here pressure versus temperature versus pressure here. Good. The vapor pressure of the solvent in the solid and liquid state. Here the solid and liquid state, this is meet at the point. This solid solvent and liquid solvent, these two curves meet at the B point, meet at this point, and here the corresponding temperature T0. Here the corresponding temperature T0 is, and the solid and liquid state have the same vapor pressure. Here, see here. Solid and liquid. These two curves meet at this point and this gives the T0 temperature and these two curves have same vapor pressure and this is known as a freezing point. Your definition is freezing point of solvent. The freezing point definition is the two solid and liquid have same vapor pressure. Here the same vapor pressure and temperature is given. That temperature is known as a freezing point or freezing point temperature. And here this is a T. It is represented, use the temperature and it is represented as T. And the freezing point of solvent has a vapor pressure of solution. This is the freezing point of solvent and then this curve, the vapor pressure of the solution is invariable. It is a less than that of the solvent. Here, solid solvent and liquid solvent. It is a less than that of the solvent. The vapor pressure curve of the solution is always lies below the solvent curve. And see here, this is a below this curve is lying below this solvent curve. And the vapor pressure curve of the solution is seen to intersect here. This solution curve is intersected here on solid solvent. Here the solution curve is seen here intersected the solid solvent at point D. This point is represented as D or is indicated as D here. This point and that is the lower temperature is given. This is a T temperature. The lower temperature is given. That is T temperature or it gives the freezing point of the solution. Here this is a freezing point of the solution and this one is a freezing point of the solvent. Here T0 and T. This is a higher temperature and this is a lower temperature. Here this point is a freezing point of solution, this point is a freezing point of the solvent. And depression in freezing point is this difference. The depression in freezing point is delta T and the delta T is already known. The delta T is equals to T naught minus T. You know this one, the delta T is equals to T naught minus T here. This is the T naught minus T. This is the rule you are writing here. Delta T is equals to T naught minus T, and this is called as depression in the freezing point. This is known as a depression in the freezing point. And here consider the vapor pressure curve E. This one. You are considering the vapor pressure curve of ED. This curve and vapor pressure curve of ED of solution. It is evident that the P1 pressure is here, presence of P1 and P. One is P1 and one is P2 here. Considering ED curve of solution, and it is evident that the P1 is the vapor pressure of the solution. Here the vapor pressure of the solution is P1 and at temperature T naught is the T naught temperature is T naught and P2 is the vapor pressure of the solution. This P2 is vapor pressure of the solution and temperature is T is given here. The T is formed here. And here you know derivation, you are applying the integrated form of Laplace equation. You are applying, you are consider this equation, this curve, ED curve, and here the solution curve, and here the pressure, the vapor pressure is P1 and the temperature is T0, and here the vapor pressure is P2 and temperature is T. I am applying on this curve the integrated form of Laplace equation. This is up to here to give the explanation of this one. I am applying the integrated form of Laplace equation. Laplace equation, and I am writing equation directly here. The ln of P1 by P2, this one, ln of P1 divided by P2 is equals to LP divided by R into delta T divided by T naught into T. I will use this one. Right here, the complete derivation of this one. Just roughly, I am writing here the diagram. This is the temperature, and this is the vapor pressure, and this one is diagram here. This is a solid solvent, and this is a liquid solvent, and this point is A, and this point is B, and this is C, and this point is D, and this is a E. And this point is E here. This is a solution curve. Okay. This is a solution curve. This is a D, and here this gives the temperature. This is a T0. This is a T. Okay. Here, first one, apply. We consider this equation, and here the P1 is pressure, and this is P2, and this is P0. Ln of this curve P1 by P2 is equals to LB divided by R into delta T divided by T0 into. This is equation number 1. You are applied the integrated form of Laplace equation. Next, here you know the LP is the heat of the molar heat of vaporization at its normal freezing point. Molar heat of vaporization at its normal freezing point T naught. Normal freezing point T naught. Okay, here considering the vapor pressure curve of AB. This one. Considering, first of all, consider this curve, this one DE curve, and next we consider the vapor pressure curve of AB curve. The AB curve, the presence of here P2 and P0. The vapor pressures are present here. One is a P0, another is a P2, and here presence of the solid solvent. And the vapor pressure curve of AB of the solid solvent, and it is evident that the P0 is the vapor pressure of the solid solvent. Here this one, P0 is the vapor pressure of the solid solvent at temperature T0, and P2 is the vapor pressure of the solid solvent at temperature T. Here also temperature T naught and T, solid solvent vapor pressure P, and the solid solvent vapor pressure P2. T naught and P2. And here also applying the integrated law for Clausius-Clapeyron equation and applying it in equilibrium cases. Here the solid vapor of solid solvent and applying here the Clausius-Clapeyron process equation. Here the ln of P naught by P2. The ln of P naught by P2 is equals to, see here, Ls divided by here Le, here Ls divided by R is here into delta T divided by here only different is Ls and here Lb and here Ls. This Lb is the molar heat of vaporization of normal freezing point T. Okay, here this Ls is the molar heat of sublimation of solid solvent. Here the Ls is molar heat of sublimation of solid solvent. Okay, this is the equation number. This is equation number. Okay, subtract equation number 1 in equation number 2. This equation subtract in equation number 2. See here, subtracting here and ln of P naught by P2, ln of P1 by P2. Here P2, P2. Okay, here R is same, R is same, Le, Ls minus here. This one is subtracting in second equation. Here Ls minus Lp divided by R into delta T divided by T naught into T. Right? Ln of P naught divided by P1 is equals to Ls minus Lp divided by R into delta T divided by T naught into, I'll write this one, and then ln of P naught divided by P1 is equals to Ls minus Lb Lf divided by R into delta T divided by T naught into T. This is equation number 3. See here, this is equation number 3. Equation number 3, where Ls, this I written here, Ls minus Lb is equals to L. Okay, this is the molar heat of fusing. Ls minus Lb is equals to Lf. I taken Lf in place of Ls minus Lb. because here this NF is the molar heat of fusion, of the solvent. Knowing that here the T naught and T are close to each other and the solution being diluted, here this equation becomes, the equation 3 may be written as ln of P naught by P1 therefore is equals to LF divided by R into delta T divided by T naught square. Here, ln of P naught divided by P1 is equals to LF divided by R into delta T divided by T naught square. This is the equation number 4. You know the equation in last derivation, elevation to the boiling point. You know here, consider ln of here ln of P naught divided by P1 therefore is equals to minus ln of P1 divided by P2 minus ln of P1 divided by P naught, therefore it is equals to taken common here minus ln and 1 minus P naught minus P1 divided by P minus ln here 1 minus P naught minus P1 divided by okay, you know one formula here. Therefore, the ln of 1 minus x is equals to minus. You consider here 1 and this is a x. This is a x and sign is minus here. Minus P naught minus P1 1 minus P naught minus P1 divided by P. Taken as here ln of 1 minus x is equal to minus x minus and this minus P naught minus P1 divided by P naught. Finally you get ln of P naught divided by P1 is divided by P naught is equals to n by n, small n by capital N. This is of equation number 6. I'll write here this one according to Rowe's law. According to Rowe's law. According to Rowe's law, ln of this one P naught minus P1 divided by P naught is equals to n divided by n plus n, and it is where compares to very small, and this is written as n divided by n. This is equation number 6. That is equation number 6. Next, from equation number 4 and 6, this equation and this equation, substitute this. What happens here? Ln of P naught by P1 value, here ln of P naught by P1, here P naught minus P1 divided by P naught, and the P naught divided by P naught minus P1 divided by P naught is equals to n by n. I'll write here the equation number 4 and 6. This one ln of P naught by P1 is equals to LF divided into delta T by T naught square. Here P naught minus P1, this ln of P naught by P1 means P naught minus P1 divided by P naught is equals to this one is equals to LF divided by R into delta T divided by T naught. I have applied this value ln of P naught by P1, P naught minus P1 to P naught. Here ln of P naught divided by the equation number 4 happens. Gives P naught minus P1 divided P naught is equals to LF divided by R into delta T divided by T naught square. You substitute this value P naught minus P1 divided P naught is equals to L divided by here. I write here this value here. This P naught minus P1 divided by P is equals to N by N. Is equals to N by N is equals to LF divided by R into delta T divided by T naught. Up to here, the equation number 6. Here, you take this side, the delta T, what happens? The delta T is equals to L by N into LF. Here, the L by N into R T naught square divided by LF. This is equation number 7. Here, this is the equation number 7. This is equation number 7. And this side delta T is equals to N by N multiplied by R T naught square divided by L. Here the delta T is directly proportional to N by N. This is equation number 8. In last derivation also here same. And this derivation also similarly. Finally, we get the equation number 8. This one is written as this one. Okay, delta T is equal to N by N R T square divided by L. Right, this type also. Delta T is directly proportional to the L by N. Next, I have this for continuation, derivation. Here, equation number 8. Okay, here the equation number 8. Delta T is equals to N by N. This one. Delta T is equals to N by N into R T naught square divided by L F. And here you substitute finding the molecular mass. Here you are finding molecular mass. You take N9, W1, W2, M1, M2. Here it is the W gram of solute. Here the W gram of solute of molar mass M. W gram of solute of molar mass M. Okay. And is dissolved in W gram of a solvent, W gram of a solvent, and molar mass M, molar mass M. And then the equation number 8, I will write this one, equation number 8. This is the equation number 8. Then equation number 8 happens here. You write here N is equals to small w divided by small n, and capital N is equals to capital W divided by capital M base B These two values substitute in equation number 8. Delta T is equals to N by N means W by M whole divided by capital W divided by MM into R T naught square divided by L. On this, you can write here the delta T is equals to this is in numerator, it is multiplied here. The multiplied means M is this side and W is denominator. Here finally get W R T naught square divided by W R T naught square divided by W M capital W M L CL. This is a capital L F. This is a small L F. And right here L F. Okay. Delta T is equal to W R T naught square divided by capital W small m and small L F. Here L F means in class derivation you taken L. It is replacing L small L. Here the LF means capital LF divided by sorry. This one is this L because this is substituted in this equation. Here delta T is equal to W R T naught square divided by capital W small m and small LF. This is equation number 9. Equation number 9 where LF is equal to LF divided by M2. This is the heat of fusion per gram of the solvent. This LF is the heat of fusion of per gram of the solvent. This is the equation number 9 here. This is that one. This is equation number 8 and this one equation number 9. Well, here we taken the W by M is 1 and capital W is 1000. Here delta T is equal to W R T naught square. This W by M is 1. This one. This is 1. And this is 1000. Small w is equal to 1000. Here the 1 mole of a solute W by M, the 1 mole of a solute W by M is 1. Is dissolved in 1000 gram of the solvent. Here 1 mole of a solute is dissolved in 1000 gram of the solvent. 1000 gram is capital W is equal to 1000. 1000 gram of the solvent. And equation number 9 becomes, and love this one. Here delta T is equal to this one. W by M is 1. Remaining R T naught square divided by W by M is 1 divided by W means 1000. 1000 into L. 1000 into L here. And this is equation number 10. This is equation number 9 and this is equation number 10. Here the delta T is equals to R square divided by 1000 into LF. Here where delta T is called molar depression constant. Here delta T is called molar depression constant. You know in boiling relation in the boiling point relationship of lowering of vapor pressure, the molar elevation of boiling point. Here the molar depression constant. In that molar elevation point constant. Here molar depression constant. Delta T is the molar depression constant and it is denoted by Kf. This one is denoted by Kf. In elevation in boiling point that is denoted as Kb. Here it is denoted as Kf. This is denoted as Kf of the solvent and this is also called as cryoscopic constant. This is also known as cryoscopic constant. Cryoscopic constant. See students, here the cryoscopic constant. The cryoscopic constant is very important for 1 mark question. Freezing depression in freezing point 1 mark question. In examination when asked the question the define molar depression constant you write same definition or define cryoscopic constant you write same definition. Here it is denoted by Kf. In the elevation in the boiling point, here the elevation in the boiling point it is called as the embryoscopic constant. Here cryoscopic constant. Okay, the definition of cryoscopic constant and it is defined as the depression in the freezing point. I write here the definition of this cryoscopic constant very important for 1 mark question. Okay. The depression in the freezing point, you write the depression in the freezing point. The depression in the freezing point which may be theoretically produced which may be theoretically produced by dissolving 1 mole of any solute. By dissolving 1 mole of any solute. By dissolving 1 mole of any solute in 1000 gram of the solvent. In 1000 gram of the solvent. This is known as cryoscopic constant. You write in your examination 1 mark question up to here. The depression in the freezing point which may be theoretically produced by dissolving 1 mole of any solute in 1000 gram of the solvent. Okay, see delta T is equals to R T naught square divided by 1000 LF. It is known as molar depression constant and this is written as Kf. Denoted as Kf. Okay, I'll write here the Kf is equals to R T naught square divided by 1000 LF. This is equation number 11. That is equation number 10 and this is equation number 11. Here up to here you write the relationship between depression in the freezing point and lowering of vapor pressure. Up to here, to write this equation. Up to this equation and molecular mass. I will continue up in molecular mass in next class. Okay. Here, since here R is a gas constant, here the R is a gas constant, and T naught is the normal freezing point. Normal freezing point, and LF is the heat of fusion per gram of the solvent. Heat of fusion per gram of the solvent, and all quantities on this right hand side of the this equation is are constant, and hence here the Kf is constant for a given solvent. I stop here class only, and I will continue after the finding the or determination of molecular numbers. I continue next class. Thank you.